This subject is linked to what Olivier was telling us this morning. And the basic question is this. We usually have a Poisson structure in the space of lax matrices, and it's a connection. And now how to extend this Poisson structure to the sections or to the wave functions of this vector bundle with connection. And there are special cases of this question when your lax matrix is a first order matrix differential operator or difference operator or higher order differential or difference operator. And in particular, the second order differential operators are related to Virasoro algebra, and if you switch to difference operator, then you get Q-deformed Virasoro algebra, and it's still slightly subtle question, how does it emerge and why is it rigid? Why the definition cannot be modified. And talking on Virasoro algebra, you can start with Virasoro algebra, and a more general thing to do is just to use Dirichlet-Sokolov reduction, which accounts for W algebras and higher rank keys. And now let's start with this case of current algebra on the line. So we have a first order matrix differential operator, and we know that the space carries a natural Poisson bracket, which is the Schwinger bracket, or is associated with the sensor extension of this current algebra, and there is a natural gauge action on this extra gauge term is of course related to the center of extension, this gauge term. Well, anyway, it's this one. So if we just look at the space of wave functions, then we have a natural projection which assigns just to the function psi's logarithmic derivative, which gives you the potential. And we want this mapping to be Poisson. But unfortunately, the arrow goes in the wrong direction. We have to suggest some Poisson bracket for psi's, which will give us the correct bracket for the potentials. And according to Gervais, Niveux, and Babylon, one can look for this bracket in this form with some R matrix. And this R matrix, well, we have a natural right action, just rescaling of wave function. You can multiply it by some constant matrix on the right. And it would be natural to expect that this bracket is invariant with respect to this simple right action. And then we can just, the natural guess is just to take just the sine function, or it's the kernel of this d-1 derivation operator. And we can also write this as a singular integral operator using the Fourier transform, and then it's quite clear that we have to regularize this operator because of the constants which do not have a natural primitive. And the correct way to do it just introduces some peculiar symmetry breaking. One has to take to subtract the constant term, basically, so this principal value integral just corresponds to the subtraction of the value at the origin, and this is just the constant R matrix which acts in some way on the. Yes, thank you very much. This regularization just introduces some kind of symmetry breaking, and then this R matrix is not quite arbitrary because it satisfies this very well-known relation, and then we just take the first and the second derivative of our R matrix, then we end up with the correct Schwinger Poisson bracket with this Casimir term before the delta prime function, and the R matrix cancels out. But this means that the right action of the this rescaling of change of the basis in the space of solutions, this action is no longer a Hamiltonian action. It becomes a Poisson group action, and this finite dimensional group has to be equipped with a non-trivial Poisson bracket related to this R matrix, which we have introduced more or less by hand in order to regularize our exchange R matrix. Now let's look at the generalization of this picture to difference operator. Just in an abstract setting, we suppose that there is a Lie group equipped, this broad face Lie group, equipped with some automorphism, and there is a group of quasi-constants which are fixed by this automorphism, and then we have this abstract auxiliary linear problem, which is for a given matrix L. We want to find this wave function which satisfies this difference equation. And then the gauge group acts on psi's by left multiplication, and on L's just by these lattice or just finite difference gauge transformations. And the quasi-constants, they act by right multiplications and leave the potential invariant. And there are just several important realizations. Just we may think of functions on the lattice, and then tau is a shift operator, or we just may think of functions which are defined in punctured plane with two essential singularities at 0 and infinity, and then this tau automorphism is just acting as a Q dilation. And one more example, which I didn't put on the list, is just additive translation on the line. So we have functions on the line, and tau is translation by, say, by one. And in the first case, the group of quasi-constants consists of constant functions on the lattice, and in the second case, it consists of elliptic functions associated with this multiplicative version of an elliptic curve. Now, the gauge action is Hamiltonian in the differential case, and in the difference case, it's not Hamiltonian. And the natural way to put everything into a Poisson context is just to start with some Poisson Lie groups structure. So we need some classical R matrices, which at this point are introduced by hand, and then we shall restrict the choice of these R matrices by imposing certain restrictions. So just since we are dealing with left and right translations, the natural thing to write is just to express our Poisson bracket as a sum of two terms. This bilinear form of left differentials plus bilinear form of right differentials, and in each case you need some classical matrix as Q-symmetric operator which satisfies some constraints. And now the definition of left and right gradients is of course fairly standard. Here it is. And if we just write this in a tensor form, then we can write it in this way, where L and R are just tensor kernel associated with this R matrix, or maybe distribution kernels if you have some parameter. This is a kind of abstract version of the exchange algebra. In the differential case, the left gauge action is Hamiltonian, and then if you just if you look at this formula, and we can just look at left and right translations acting on psi, which corresponds just to gauge action and to this change of basis, which is ultimately related to the difference Galois group. I'll just say a few words on it later.
This element is infinitesimal translation.
Just in my examples, just we have this finite lattice. It is lattice realization or just function difference realization. Just this is Q difference, and also I can just genuine difference operator just acting on the line. That's another example which I failed to put on the blackboard. If we just look at this formula, sorry, it's too sensitive. So we have this left action, which amounts to gauge transformations, and right action. And then this group of left translations and right translations, they give you Poisson actions with, if you just take a group G L times your space of wave functions into wave functions, G psi acting into G times psi. This action is a Poisson action if the gauge group itself carries a natural Poisson bracket, namely this Kleinian bracket associated with this left R matrix. Poisson action when G L is equipped this Poisson bracket is just this Kleinian bracket associated with this left R matrix. And there is another bracket G R acting on W into W. Psi goes into psi times H. And this is again a Poisson action if this right group is equipped with another Poisson bracket associated with the right R matrix. Now, if we just come back to the differential case, then of course the gauge action is Hamiltonian, which means that the Poisson bracket is invariant with respect to this gauge action. So the left R matrix is then trivial, and we are left up just with right R matrix. This is just a degenerate case. And in the full difference case, both actions, left and right, are Poisson actions and not Hamiltonian actions. And now the choice of these two matrices is almost independent, well, just at least a priori. But we must care about the Jacobi identity, because the abstractions, they combine, it's not needed that the left matrix separately satisfies the Jacobi identity, nor the right bracket, because the abstractions cancel each other. But we must think about proper normalization of these matrices, so just as to assure that everything cancels. And now just let's look at this natural reduction. So we take this combination, which is just the potential in the auxiliary linear problem, and we look at the Poisson bracket of functions which depend on this combination. And so we compute left and right gradients of this function capital F, and after some computation, you get this formula, which is very much similar to what we have once discovered together with Alexei Fadeev and Volkov under the name of lattice current algebra. But it's important to notice that it's not quite yet the thing, because some crucial terms are still missing from this formula, and also the Jacob identity fails. And as should be expected, that the remedy comes from the right arm matrix, which will should convert this intermediate formula into something quite good. But it seems to be almost impossible to do, because this combination it depends on well, left gradient just is expressed in terms of the differential, left and right differentials of this capital F function, but by contrast, right gradient depends on psi and not on this combination. So it has to be cancelled out. And if we just make the computation of this Poisson bracket, right Poisson bracket, then we have this, where x1 and x2 are just the gradients of f, but psi is also there. And so it has to be cancelled out. This is just the condition, the consistency condition, just in this formula, which a priori depends on psi and not just on this combination, which amounts to this. Yes. This, well, just instead of laser, I shall just use the mouse. So we have this combination, and everything should depend on the gradients of this, of the function of this combination. So then psi itself has to be cancelled. And now there is a very natural condition. The only thing, this rigid condition, is absolutely simple.
What is x1 prime?
x1 and x2 are just gradients of this function f. We have function, we compute, we have two functions, f1 and f2, and then we have, they are expressed like this. It's some function f, capital F, which depends on this combination, on the reduced combination. And then we, everything is expressed in terms of the gradients of this capital F. The left gradients are called x's, just the gradient of f1 and the gradient f2, and these are just right gradients. And then it has to be cancelled. Psi has to disappear. If it disappears, then it's okay. If it's not, we don't have a consistent Poisson bracket on the quotient space. And the answer is this. The R matrix should be essentially the Kelly transform of the automorphism tau itself. So it's this formula. If we just temporarily assume that tau minus 1 is invertible, then it's this rigid formula. And if basically it's, you see here some difference, and so this formula doesn't restrict the value of R on the subspace of quasi-constants. And so we must write something like this. R is R naught plus R prime, where we have this decomposition. G is equal to kernel of tau minus 1 plus image of tau minus 1. And on this image, the Kelly transform is well defined, and this is the space of quasi-constants. So the regularization problem is associated with this natural decomposition. So if we just take this operator, which is partially defined, then it satisfies the modified Young-Baxter identity. And everything cancels out, and this right contribution is just this bilinear form, left gradient coupled to the shift of right gradient, minus vice versa. And if you add these terms to the formula which was written here to this one, then these two terms, they just combine to give you the correct lattice current algebra. So it's okay, and it fixes the arithmetics just up to the treatment of the quasi-constants. If you just write this again, we use Fourier transform to write this singular it's cotangent. Sorry, it's cotangent. Cotangent hasn't been recognized by LaTeX, and I didn't notice it. It's cotangent. It's LaTeX mistake. Yesterday I was just preparing a file, and there was the name of function which this version of LaTeX didn't recognize. I omitted the definition of the command. We have to regularize this singular integral operator, which has the cotangent. It has poles just on the real line, where the cotangent usually has just at k equal to pi times n. And so we just we use the standard way to produce periodic functions from non-periodic ones, which is used in the Poisson formula, and then this is the Poisson formula. And if we just subtract the values of the Fourier transform at the poles of the cotangent, again the cotangent it's here. So it's a principal value integral which with cotangent, and the regularized terms it just is organized into this finite dimensional arithmetics, adding on the values of the periodic function produced from the values of the Fourier transform at the multiples of pi n, effectively, because it's 2 pi n, because it's cotangent over our argument. So it's cotangent of k over 2, so it has poles at the multiples of 2 pi. So this is the formula, which is very much reminiscent of what we had with the simple epsilon function, but the kernel, the epsilon kernel, is now replaced by this cotangent kernel. And now if we just look at the Q difference case, again, we have something like this. We have this distribution kernel of this operator, which is just the action of R on this multiplicative delta function. And so here it comes, and this gives you just again a decomposition again, we just must subtract singularities. And so we do, and this R matrix, well, it's almost elliptic. It's a logarithmic derivative of theta 1. So it's invariant with respect to translations, and the second period is invariant with respect to the second period up to an additive constant. And here we have only just one singularity. And what is important in this case, again, just in all cases which we encounter, the regularization comes from just a finite dimensional R matrix. We like in this formula. In this case, the group of quasi-constants is infinite dimensional, and it's precisely the situation which was mentioned by Leon in his talk, where you have plenty of quasi-constants, but we have a little group, and this little group carries a natural Poisson structure. Essentially, it's just this finite dimensional group is nothing but the difference Galois group, which is associated with a properly defined extension of the space of potentials by wave functions. So this finite dimensional group carries a non-trivial Poisson bracket. So there is this peculiar symmetry breaking associated again with this need to regularize this singular integral operator or this singular series. This is what the same discussion is summarized on this slide. Now we can just look at the first case, which is the lattice case. And in the lattice case, this R matrix, again, the Cayley transform of the shift operator, is precisely given by this very simple formula. So we are back to the context which has been discussed by Olivier in the beginning of his talk, this lattice algebra. And the origin of this epsilon function now becomes more clear, because we have also generalizations. Just in non-trivial cases, this epsilon is replaced either by cotangent or by theta 1 function, depending on the case. T is just the Casimir. Yes.
Intended product.
Just tensor Casimir, just as usual. It's just the kernel of the unit operator, basically. We have this R matrix is a kernel of an operator, and then its action on matrix is just it's the identity action. And this action is non-trivial. On the constant term, it acts in non-trivial way. Just P plus minus P minus, basically.
About Galois group?
Well, the Galois group is implicit here, because we have this, it's this action, the right action, this one, which becomes a non-trivial Poisson action. And in this case, this right translations, well, there is a tremendously big group of right translations associated with all quasi-constants. But this group is unreasonably big. And inside this very big group is a genuine difference Galois group. And its action becomes a Poisson action. And it carries this, just generically, this Poisson group is just SON, or SO2 for n equal to 2. This is the full special linear group. And it becomes a Poissonly group. So this is particularly transparent when we look at the second order difference operator and on the Virasoro, to which I will come in a few moments. How many minutes do I have?
We can negotiate.
Sorry?
Let's say 10 minutes.
10 minutes, fine. Just on the lattice, you have another ambiguity to be resolved. There are two definitions of monodromy, just this one or that one. And they are, of course, conjugate. But their Poisson brackets are very much different, because this thing is invariant with respect to right translations of psi, and this one is equivalent with respect to gauge transformations, with respect to left translations. And so for M, it is possible to compute the Poisson brackets explicitly, and we get, it basically depends on L, and we have, sorry, it's too sensitive. We have this Poisson bracket on the for one version of the monodromy, and this is basically the dual Poisson bracket, the dual Poisson-Lie group, and this is Poisson action. It's an old computation which says that despite the fact that the Poisson bracket on the lattice is non-local, still you have a nice Poisson properties for the monodromy map. And by contrast, the other R matrix O tilde is associated with the right R matrix, and you get a different answer. Again, some sort of dual Poisson bracket, but especially associated with the right group. And there is a simple way to reconcile two formulas so as not to think much about which version of the definition of the monodromy do we prefer. If we just take R naught equal to L, which is possible, and in this case everything becomes even more simple. And now I'm coming up to Q-deformed different Sakharov theory. So we have this nth order scalar difference equation, which we can write by using some sort of companion matrices, which here can be written very conveniently in terms of this matrix S, which is now realized as just a Rayleigh translation, and this S is just this standard matrix which represents a Coxeter element in the Weil group. No, it's just a Lux operator without spectral parameter. And so this and the potential matrix, which is just this, it's a uniport matrix with ones on the principal diagonal and with just one row, and it belongs to the abelian group, which consists of all uniport matrices which change. Yes.
In the left corner, one letter should be 1.
No. It's just if you make multiplication, if you just multiply this triangular matrix from this unipotent abelian unipotent subgroup, then just make the multiplication, and you will see the companion matrix, the usual one. It's just a nice way to treat the companion matrices for different separators. It's a fact which is not probably too widely known. And if we do this, then if we just take our matrix in this very simple form, this represents a set of constraints. This companion matrix constraints. In the 2x2 case is something like this. Your L matrix is 0, -1, 1, U. And these are three constraints imposed on this R matrix. Now, in the differential case, these are first-class constraints for a trivial reason, just if you treat differential operators. But in the difference case, they are generically second class. And this would represent a disaster, because the whole description of the difference operator as a quotient space over a nilpotent gauge group would fail. So we have to insist that these brackets should be of first class. And it's an important old remark which we made together with Rüstichen and Frenkel maybe 15 years ago, that this is possible under very rigid choice of our R matrix. And namely our R matrix L must be P plus minus P minus plus rho not P naught. Because we are dealing with this triangular decomposition, our left R matrix must take care of that. It must be compatible with the gauge action of the triangular group. And so we just take it according to the Gauss decomposition. P plus minus P minus plus there is some extra liberty left. We can use the diagonal part. And this diagonal part, rho naught, is nothing but the Cayley transform it's acting on the Cartan subalgebra. And on Cartan subalgebra, this Coxeter element induces a reflection, which amounts to -1 in the case of SO2. And we must take as rho naught just the Cayley transform of this translation tau combined with the Coxeter reflection. This is a rigid answer, and it's this rigid answer which is at the origin of the lattice or Q-difference Virasoro algebra. And so this is this formula. And then accordingly our right R matrix, which has to be adjusted according to the choice of the left R matrix, is now chosen in this form. So it's P plus minus P minus plus this extra term, which is non-trivial unless your algebra is SO2. For SO2, this Coxeter reflection is just -1, so it's this term dies out. For higher case, just for W algebras, this is already an important correction term. And we can just look at the reduction in this big picture psi. We have just psi tau is equal to L psi, and psi is just the fundamental solution. It's a matrix solution to this matrix difference equation. But when we deal with the scalar case, just the difference of reduction, we need some set of scalar functions, phi, phi1, phi n, just a set of just a basis of n independent solutions of this nth order scalar difference equation. So what are these phi's? They're just given by the first row of the fundamental matrix psi. And if we impose all constraints, then this matrix, fundamental matrix, is just the van der Waals matrix, which is something like this: phi 1, phi 2, phi 1 tau, phi 1 2 in the 2 by 2 case. And so we just need to look at the first row of this matrix, and then we can compute the Poisson brackets for this for the matrix coefficients of this first row. And we can also go to the projective picture, so we can look at eta 1 equal to phi 1 over phi n, etc. phi eta n minus 1 equal to psi n minus 1 over psi n. And in this way, we just get a projective description, just a kind of projective curve with values in a projective space Cp n minus 1, which is associated with our auxiliary linear problem. And we get a correct, a well-defined Poisson bracket on this space. So this is my van der Waals matrix. And in particular, for this projective wave function, in the case n equal to 2, we get this formula. which has been once found by Fadeev and Takhtajan in the study of zero modes for Vezumina model. Here it appears in the Liouville. Yes. So here it appears just as a special example of this more general construction. And notoriously, this formula also yields a lattice version of the Virasoro algebra. And now, what is added to these old results is just the possibility to treat in a very similar way all Q difference operators, just finite difference operators on the line, or finite difference Q difference operators in the punctured plane. Well, just here is again the end of it.
Questions or comments? I've got one possibly stupid question. So in those formulas that you have with the Kelly transform, typically there are dynamical R matrices which have various Kelly transforms. Have you thought of whether this can be adapted to the dynamic?
I don't know. I must confess that I know very poorly this dynamical theory. I know that in dynamical theory the Kelly transform is also quite useful, but here it was introduced just on an independent reason, for an independent reason. And
or maybe not.
Yeah, well, just maybe not. But I don't know the answer. It's a good question.
Any further questions? If not, let's thank the speaker again.